So in our last lesson, we introduced the idea of MPLS. We discovered that in MPLS, packets are stored based on the value of a label rather than the IP address. We also discovered that the label switch path is really set up on the ingress router initially, where the path is described by giving it a name, specifying the IP address of the egress router, and also specifying the value of the very first label that's going to be pushed onto the very first packet in that path. We also discovered that we have transit routers that will do a lookup based on the label value and forward traffic based on that value, and they'll also swap the label for a new label and put that new label onto the packet before it is forwarded on to the next router. We also discovered that, as a usual thing, it is the penultimate router that will pop the label and then forward that packet onto the egress router without any label at all, and the egress router will forward the packet based on its IP address. So we also looked at the process of setting up a static label switch path, which you will do as part of your first lab. We're going to look at our label distribution protocols, and these are absolutely amazing in that they will go ahead and create a label switch path for you, and all you need to do is simply tell them where you want that path to go, and they'll go ahead and configure up your routers for you and create that path. So let's take a look at how these signaling protocols, as they are usually referred to, let's take a look at how these signaling protocols work. So we're going to take a look at the two common label distribution protocols, which are RSVP and LDP. We're going to identify the configuration elements used for those signaled LSPs, RSVP and LDP, signaled LSPs. We're going to identify the label distribution protocols that can meet the constraints and configure an LSP when given a network topology. The ingress router and egress router and path constraints. So we're introducing this idea of constraints. We will kind of into a whole lot more detail around the idea of constraints as we go on into our next lessons. But let's take a look at these signaling protocols. So the two are RSVP and LDP. Now RSVP has been a protocol that's been used for many years before MPLS, actually, as a resource reservation protocol. So it's used to reserve the resources on systems and devices, mostly systems and devices. But it has been adapted to be used with MPLS, and it is very effective in use with MPLS. The LDP label distribution protocol has been designed specifically for MPLS. Okay, so label distribution protocol, often referred to as signaling protocols, dynamically establish a LSP. And they do that through exchanging label information between the routers that are forming that label switch path. The Jupyter operating system supports two types of protocols, as we've already discovered, RSVP, or Resource Reservation Protocol, and LDP, or Label Distribution Protocol. To reduce confusion in this course, we're just going to use the acronym LDP to only refer to the Label Distribution Protocol, because LDP can refer to other things as well. Okay, so RSVP, I guess this is the major difference between the two. RSVP is used for traffic engineering, LDP is not. Okay, so one of the great things we can do with RSVP is we can say to our protocol, I want you to create me a label switch path that goes from here to here to here to here. We can specify the path that is taken through the network with RSVP. We can't do that with LDP. LDP always follows the IGP best path. You think, well, what is the use of that? Okay. Well, it's absolutely no use if your goal is traffic engineering. So if your goal is to be able to define the path taken by the LSP, then LDP is not going to help you. You're going to have to use RSVP. So RSVP is in fact the internet standard for reserving resources. It's been extended to support explicit path configuration, which means go here, then go there, then go there, then go there. That's explicit path, so telling the LSP exactly which routes it's going to go through. Path numbering and route recording, so you can record the path that traffic takes as it transitions the label switch path. Route recording. It also provides keep alive status for visibility and redundancy. LDP always follows the IGP best path, executes hop by hop, and does not support engineered paths. It does have a use, which we will get into much later. Okay, so let's look at RSVP. It's a generic quality of service signaling protocol. It's used for other things. It's used for lots of other things besides MPLS. An Internet Control Protocol uses IP as its network layer, designed originally for host-to-host usage. It's not a data transport protocol, and it is not a routing protocol. It uses the IGP to determine the path. So when it's building a label switch path for you, it will look at the IGP routing information to determine reachability and connectivity between all the routers in the path. So the RSVP sessions use unidirectional data flows. So go in one direction. The ingress router initiates the connection. That's a very important point, that the RSVP configuration for a label switch path is always done on the ingress router for that label switch path. The RSVP uses what's called a soft state, which means that these resources are reserved, but you need to periodically refresh the reservations that you made to keep them active. If you don't refresh them, they'll drop out and the path will then be terminated. Okay, so it has this mechanism built into it where it periodically refreshes the path that it's set up. That's actually a good thing as well, because we are dealing with networks, we're dealing with provider networks that potentially could be within the same building, but potentially could also span hundreds of miles and have fiber links in between and all kinds of things. So things can happen, right? Things can happen in a network. Links can go down. And so one of the really great advantages of these signaling protocols is if a link goes down, they can re-signal the path for you by another path, by another route. So they can bring up your label switch path automatically for you. We'll get into that, looking at how all that can work later on. So have their soft state, so they maintain dynamically, can change during the life of the session. So we can re-signal the path to go somewhere else. Path messages are sent downstream, and reservation messages are sent upstream. So what happens is we start off on our ingress router, and we configure up our RSVP protocol session to create a path for us. So what happens is we're saying to the protocol, I want you to create a path from R1 to R5, and you can put other things in there as well. You can say, I want you to go via a particular router, or I want you to want a certain amount of bandwidth. There's other stuff that you can specify as to what this path must have or where it must go. I could say, well, I want this path to go via R3. I could do that. I wanted to. Why, but could. So you can put information into where you want this path to go, and what it will do is it will then use the IGP to find the links or find the connectivity along the path. So it goes along and it sets up this path information on each and every router that's going to be in the path, and then it comes back the other way and reserves resources on the router on the way back. So it sets up on the resources. As it comes back, it'll reserve things like bandwidth. It'll set up your label values that are going to be used for the swaps all the way along the path. Okay, the sessions are signaled by RSVP messages, and there's a bunch of different messages that the protocol uses, including a path message, which is a request for the LSP to be created, a reservation message, which is reserving resources for the LSP, and I mentioned resources are things like the label values, bandwidth, maybe other things. Path tear, which gets rid of a path, so we don't need it anymore, tear down a path, or maybe a link has gone out and we need to re-signal the path. So a path tear, and then a reservation tear sort of goes with that. There's also path error messages where we get to a point where the path can no longer be established. Path errors and reservation errors. Or maybe we can't. Maybe you've said, I want you to create a path to this particular egress router, and it can't create a path to that router for some reason. So these messages are comprised of RSVP objects. So state, it's a soft state, so it requires this periodic refresh to keep it alive. We have information contained in a thing called a state block. It's a block of information, and a reservation block. So there's information contained in these things called blocks. A state block or an information block is just a little chunk of information that is stored within the router. That is called a path state block, and we have a reservation state block. So once you go on to, so what you're going to do is we're going to go on to the ingress router, and we're going to say, I want a path from here to there, and you can put other things in it as well, like go via here, give me a certain amount of bandwidth, all those sorts of things. And then RSVP goes ahead and builds a path for you, and it will actually go and configure up all the other routers that are going to be involved in the path. So you don't have to go and create a static LSP, it will create a dynamic LSP for you. So the extended RSVP, which has been extended for MPLS, has a hello protocol and label distribution information. It's now used for router-to-router connectivity. So path message extensions, things like we have a session object, so we have a tunnel, we have a label request. We can also put in things like an explicit route object. That's a very, very interesting piece of information there, because what that says to the protocol is this path has to go between this router and that router and that router and that router. That's where you define where your path has to go. So that's where we get to do this traffic engineering we talked about right at the beginning, is we can tell the traffic where it needs to go through our network. We have these things called strict hops, and forms a network of the exact path to use, or a loose hop, which says the LSP must be transited in order the IGP is then used. So a loose hop says, the strict hop says, well, it puts all the different hops along the entire path, whereas a loose hop doesn't. It allows the LSP to go through one particular router, but then use the IGP to determine the rest of the path. Record route object lists all of the labels routers that the LSP traverses. We have session attribute object aids in session identification, also control setup priority, holding priority, and local rerouting features. Remember earlier on I said you can have path priority, so you have some paths that take priority over other paths. So that if there is, say, congestion on the network and you can't maintain some of the paths, well, we have high priority paths, which means the lower ones will just get torn down. And that traffic will, oh, sorry, it's not going anywhere. So you're able to prioritize paths. And there are setup priorities and holding priorities. So a setup priority is where I'm setting up a new path, I'm giving it a high setup priority. If its setup priority is higher than another path's holding priority, and there's not enough bandwidth for both, guess what? The one with the holding priority that's lower than the new setup priority, it's going to get shut down. You're going to shut down that path. We also have these local rerouting features. They are designed to deal with link outages. So we drop a link and then we can reroute our LSP around the failed link. This LSP hop object, just information, contains the previous hop address, which means we can just we can query that information. So the path message, explicit route is passed by R1. So R1 transmits a path message addressed to R5. The label request object request label binding. So we put in here an explicit route object, and we're saying we're going to go through R2, R4, and R5, and that is all strict routing. So we are saying this is the path, and it will not go anywhere else except via this path. Record route object lists the nodes visited, so we can, that's also very useful. And the session object uniquely identifies the LSP, RSP hop indicates the previous hop address, and the session attributes priority, preemption, fast reroute, talking about that, for dealing with link failures. And we can also use this sender tspec object here, which is a bandwidth reservation. So I can say that my path must have a certain amount of bandwidth. So that's going to be determined by the traffic that's going across that path, how much bandwidth you want to reserve for it. Or it may be determined by a service level agreement that you have in place with your customers, where they require a certain bandwidth. And you can set that up as part of your path. Reservation message extension, that is session object, identifies the LSP, is the name of it. Label object, upstream, performs the upstream on-demand label distribution process. And the style object specifies the reservation style. Is it fixed, filter, wildcard, shared? There's a few options there to look at. And then we call route object we talked about, and the hop object. So reservation message processing, R5 transmits a reservation message to R4. So what's happened is the path message has gone from R1 down to R5, and now R5 is going to signal back the reservation message coming back up. So R5 will transmit message to R4. The label is 3, which indicates that penultimate LSR should pop the header. So what R5 is doing is saying you're going to have a label value of 3. which is going to be sent to you. That's what it's informing R4. Session object identifies the LSP, the name of it, RSP hop, previous hop, record route. All that is sent from R5 to R4. R4 and R2 store the outbound label and allocate an inbound label. That's all configured by RSVP. The label values are configured by RSVP. So that each router gets its label value by the reservation. The reservation message figures up the label values. And R1 binds the label. So the reservation message on R1 will actually R1 will actually set the initial label value on R1. So a path error message will occur if a path cannot be created. So R4 cannot signal the LSP. So it actually can't create. So there's no. So you've said, well, this path must go from R1 to R2, and then to R4, and then to R5. But for some reason, there is no connectivity between R2 and R4. It'll send a path error message saying, no, alright, I can't create the path you have requested. And a reservation error message will come back and say, I can't reserve the resources that you've requested. Maybe you've requested a bandwidth which simply is not available. And so you get a reservation error message for that reason. And then there's these path tear messages which occur in the event of a link failure. So the path has been set up, everything's good, but then something happens, we have a link failure, and we get a path tear message. Or it could be that the path has been preempted by a higher priority path. And that would also result in a path tear message. Okay, a label request object indicates that a label binding is requested for the LSP, and this contains the LAN 3 protocols. This is the show RSVP trace options. We're looking for RSVP send. Explicit route object. This is really very useful. If we take a look at that, we'll see that we have got the IP addresses of the routers in our explicit route object. So we've got a strict route, and so we've got a loose route in that particular message. So S and the L. Okay, that. The record route object keeps track of all the routers on the LSP path. So we've requested that the route be recorded. We can query that and actually get a output by monitoring the path that the traffic takes. Reserve message objects. This is some examples of them there. They can contain a number of different RSVP objects. Some IDs there. We've got different styles, different label types, record route objects. So this is showing us the whole path through which the LSP is going. We can, of course, configure trace options on RSVP and log that information. So we can go back and take a look at the log of our RSVP protocol. And in this case, we're looking at a file that's called RSVP trace options, and we're looking at everything, flag all detail. Okay, this is a little bit about MTU discovery, which is, of course, maximum transmission unit discovery on RSVP signal to LSP. So this function prevents issues with traffic being black hole when the ingress MTU exceeds the MTU of a path element. So we may have the MTU on the ingress router being higher than the MTU of another router in the path. So as part of the path message, it will go through and examine the MTUs on all of the routers in the path and deal with that issue so that we don't end up sending packets that are too big. It uses the ACIT object as per the integrated service object defined in this RFC 2210 and 2215. Configuration options for MTU discovery are available within the protocol, and fragmentation in ingress LSR. So we can adjust the packet size at the ingress LSR. MTU discovery and fragmentation, we can take a look at that there, show RSP session detail, and you can see we've actually configured that. And we've got an MTU path proceed of 1500. So we take a look at the ingress router is actually 440, but we go down to R4, we're down to 1500, and so we've actually received that information. We can set up authentication if we want to within our RSVP, so that's something we can set up as a security mechanism on our network. And we can also use it with a graceful restart. If we have a router that's restarting, we can use graceful restart in conjunction with RSVP so that our forwarding plane will keep working while we're restarting our routing engine. So traffic will essentially not be dropped if the routing engine is restarting. Okay. So let's take a look at how we configure this up. We're going to be configuring this on our ingress router. So the signaling protocol is always configured on the ingress router. All the other routers require the appropriate interfaces configured under protocols RSVP and protocols MPLS. So what we're saying is that the actual label switch path is set up on the ingress router via the signaling protocol, but all the routers in the path must have RSVP and MPLS enabled on all the interfaces that are participating in the label switch path. Okay, so here we have our configuration, functional RSVP configuration. We need the MPLS family on the required interfaces, on the loopback interface, linking interfaces with the router's MPLS process, enabling RSVP on the desired interface, configuring label switch path under the protocol's MPLS hierarchy. So here we have, let's look at our interfaces. We can see we've got family MPLS on the interface, and under edit protocols RSVP, you reference the interfaces that are going to be used for that protocol or going to participate in the label switch paths that will be created by RSVP. And there's our edit protocols MPLS, again with our label switch, with our interface referenced, and also our label switch path is referenced in there as well. Now we're going under this is our explicit route object. So under our edit protocols MPLS, we can go ahead and configure an explicit route object. The name of it is through R3, and then we have said that this is our path 192.168.1.3 loose. So what we're saying is this label switch path must go through R3, but we're going to rely on the IGP for how the path actually gets to R3 and then where it goes after R3 on its way to R5, which is our egress router. So we're going to let the IGP make those decisions, but what we're saying is it has to go through R3, which is 192.168.1.3. We can have point to multi-point LSPs as well, with multiple destinations, single ingress, multiple egress. Now, when we get into multicast, we'll spend a bit of time on multicast. We'll see a lot more about how this works. This is packet replication happening at R2. So what we've actually got there is multicast happening within the MPLS network, and this would typically be used in the case of something like IPTV or internet-based radio. I know of a local service provider that provides internet radio distribution, and they actually use multicast to distribute the internet radio through the network. Okay. So this is the these are our point to multi-point LSPs. So essentially, we have got packet replication happening in it. We'll get into that in a lot more detail when we do our multicast. I won't spend too much time on that now. Okay, RSP operational mode commands. So clear the session, show the session, clear the MPLS LSP, show it, and show the RSPP interface. That's our monitoring commands. So this is an example here. Show RSPP session detail transit. So here we are looking at R2, which is the transit router, and we can take a look at the session details. And then this is R1, show MPLS LSP ingress extensive. We're taking a look at that information. A lot of stuff there we can see. We've got a record route information there. We can see the path through which the LSP is going to go. So a whole bunch of information. Alright, so that's RSPP. We'll do a lab on this, and we'll get into figuring out and see how it works. Level distribution protocol designed specifically for MPLS. Creates a thing called a forwarding equivalent class. Group of IP packets that are forwarded in the same manner, manages the LSP to the egress router, and LDP associates the FEC which each LSP creates, or forwarding equivalent class. Creates a LSP tree for each FEC from every possible ingress router to the egress router. So essentially it follows the IGP best path. And hello messages, TCP session establishment, label request messages, label mapping messages, got a hello base native discovery. So essentially, it will go ahead, and what it's going to do is establish a LSP between every router on the network on the way to the egress router. It's actually used a fair bit when we're dealing with multicast, because that's where we do in fact want LSPs to pretty much go around almost every link in the network, and we're going to be distributing our multicast traffic across those LSPs. Okay, so we start off with a three-way handshake. We initialize the session, and then once it's up, we use keep alive to keep that session up. Downstream peers will assign the labels. So the traffic engineering information is not piggybacked on routing protocols, limitations. LSPs always follow the IGP path and does not support explicit routing. So we can't do traffic engineering with LDP. So the sessions are maintained using hello packets, hello intervals 5 seconds, a hold timer of 15. If the hold timer expires, then the LSR deletes the adjacency as well. The important things here: interface addresses and users router IDs. So Juno's operating system supports version 1. Sort of looking at the main points here. We're going to go ahead and set this up as a lab. We're not going to do too much with it in actual fact, because what we are more interested in is actually the traffic engineering aspects of it. So we're going to go ahead and we'll set it up to see where we can go. We're not going to spend that too much time on it. What we can do, we can set up LDP over RSVP. So LDP views the entire RSVP LSP as a single hop, and it will traverse the RSVP LSP instead of using the 2 hops through R3. So you can actually run both protocols over each other and set up a LDP single path over an RSVP single path, and can use authentication on this as well. So use graceful restart, and it's verifying the LDP session there. So LDP configuration topologies, looking at verification commands. Let's take a look at that. So there's a functional LDP configuration involved enabling LDP on all the desired interfaces, adding the MPLS family to the interfaces. Don't worry about the loopback address, linking the interfaces with the routers and MPLS processes. So here we have got show protocols LDP, there's our interfaces referenced, show protocols MPLS, we've just got all, and on the interface itself we have configured the family MPLS statement, which we're going to need. Show LDP interfaces, this is our monitoring. Show LDP neighbor, we'll see our neighbor routers, and that's our session information. We can verify the routing information by doing a show route table INET3. Now, remember, it's INET3 that is used by BGP when it's directing traffic into the label switch path. This is our label mapping, show route table MPLS 0, you see the label mappings that we have got there, show LDP database, and we'll take a look at all the different routers along path. Okay, so we'll do a lab on LDP, just want to see how it works, but we're going to spend most of the time with RSVP, setting up traffic engineering. So have a look at these 2 signaling protocols. And what we discovered is that they will dynamically create a label switch path for us. We also discovered that with RSVP we can do traffic engineering, and we can create these things called explicit route objects that determine exactly where the traffic goes through our network. We can also do things like reserve a certain amount of bandwidth that we want for our path. We can put in a thing called a record route object, which then records every router through which the traffic passes on its way through the label switch path. We can go and take a look at that information to verify that our traffic has taken the path that we wanted it to take. We can do other things with RSVP, like we can set it up so that it can reroute traffic in the event of a link failure. We'll get into that in a bit more detail. So we had a look at these capabilities of these label switch, of these signaling protocols to go ahead and automatically create a label switch path. So let's look at some review questions. Which router requires you to define the label switch path when configuring RSVP? So the question is asking which router in the path. Is it the ingress router? Is it a transit router? Is it the penultimate router? Is it the egress router? On which router do we configure RSVP when we are configuring a dynamic LSP? ingress, transit, penultimate, or egress. On which route do we configure the RSVP protocol? Now, bearing in mind that we have enabled the protocol on all of the interfaces, that on all the routers that are going to be participating in the label path. So we have to enable it, but when we talk about actually configuring the path is configured on the ingress router. Okay, on the ingress router. 3 RSVP objects that we discussed. Well, we talked about this thing called an explicit route object. We talked about a thing called a record route object. And we also had this thing called a TSpec, which really deals with bandwidth. So we can say we want a certain amount of bandwidth. And does the Junos operating system support traffic engineering on LDP LSPs? Well, that's just a yes or no answer. So you have a 50-50 chance with this one. Does it or doesn't it? Can we traffic engineer with LDP? Yes. 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 Okay, guys. The answer is no. We cannot.
Amazing.
The answer is no. No. If you want to do traffic engineering, what signaling protocol do you have to use if you want to do traffic engineering? What signaling protocol must I use for traffic engineering? It's called RSVP. Okay, that is the name of the protocol, RSVP. Alrighty, so what we're going to do next is we're going to get stuck into some labs. So we're going to get just get started with configuring our router and just making sure that we've got this basic connectivity up and running. Okay, because I want to sort out really quickly any issues that you're having with just making sure that your pods are working. If you can get connectivity from your MX device to your VR device, that's the first step. Let's just get that happening. Let's configure up OSPF and make sure then that we've got connectivity between MX1 and MX2. Okay, so both ends. And then once we've got that up and running, well, we're pretty much sure that we can go ahead and get everything else working after that. Alright, so everything else will work. I just want to get that done first and make sure that we have that. So we will now get stuck into some labs for the rest of the day.